Good morning, everyone. Today we're going to present our research, and our research topic is Voronoi model of tissue structure. And first, I'm going to introduce my team members to you. First is Emily Dorazi, Alex Loretti, and Professor Silvia Jimenez Bolanos. And we're representing Korea University's mathematical problem-solving class. And first, I'm going to give you a brief introduction of our project. First, our academic sponsor is Mathematical Association of America, and we're working on this PSC Math project, which stands for Preparation for Industrial Careers in Mathematical Science. And we also have an industry client, which is DECA, and it is a New Hampshire-based company that focuses on the development of new technologies and their applications in the medical devices industry. Then I'm going to talk about our motivation for this project. So first, in current days, regenerative medicine is a useful way and to attempt to use a patient's stem cells to restore, maintain, or improve damaged organs or tissues. And the tissue regeneration process requires us to predict the way cells expand and multiply. And we believe Voronoi diagram is a useful way to do that because it can partition a two-dimensional plane or three-dimensional space into regions based on distance on a specific set of points or centers. And we also believe that Voronoi diagrams provide us with enough information about the number of sides, perimeters, and areas of Voronoi cells, which can be used to model the geometry, forces, and dynamics of cell growth. And then I'm going to give you a brief description of our project. So first, our research project centers on the problem how to predict the path growing tissue will follow as cells expand and multiply. And we figure out there are a few steps of our solutions. First, we did literature search. And through literature research, we've learned that past researchers have used Voronoi diagrams to model the cell regeneration process. So we think it's a good way to represent the geometry, physics, and biology behind the process. We also use MATLAB to generate our Voronoi diagrams because three reasons. First is it's the most accessible programming software in our math department. And second is our past courses, such as numerical analysis, has taught us to use MATLAB, and we're very familiar with the language and syntax. And MATLAB also provides us with a few built-in functions to generate Voronoi diagrams, which help accelerate our coding process. And the last point I'm going to mention is the point generation process via uniform random process, which was this way because we believe is the most representative and direct way to simulate cell regeneration. And now I'm going to turn to Alex to tell you about our procedures.
First, I just want to give a quick overview of our procedures. So the first step we had to do was to create and define a medium for testing. So we had to create a Voronoi diagram in a bounded region. Then the next step was figuring out how to adjust an individual cell's perimeter and figure out a method to do so. And then we needed to apply that method to equalize all cell perimeters in a given Voronoi diagram, and then compile the data from multiple trials for statistical analysis. So when creating the testing medium, our objective was to create a bounded Voronoi diagram within a bounded square with 100 random points. And so to do this, we downloaded the following program, Polytope Bounded Voronoi Diagram in 2D and 3D by Hanju Park, which essentially created what you see in front of you right now, which is a Voronoi diagram in a bounded region, which we set to be a 1x1 bounded square to ease the statistical analysis. And then an important choice we also made was that we decided to discount the boundary cells here that you see on the basis that in nature you don't have a boundary. And so by only counting the interior cells which border other cells, it is a better representation of what you see in biology. Allowing these border cells to move allows the interior to have a moving boundary that essentially represents boundary cells. So the next thing I want to talk about is our method of adjustment. So the initial problems we faced were that Voronoi diagrams there is no specific algorithm that exists currently to adjust the perimeter, adjust it, to increase or to decrease the perimeter. So we also couldn't move just a single boundary neighbor, because any neighbor moving inward or outwards does not guarantee increase or decrease in perimeter, as it has a rippling effect on its neighboring cells. So by moving just one, you might be decreasing its perimeter of the side that's directly adjacent, but you might be increasing the bordering sides. So our way around this was to just move all the neighboring centers at once. And so I've drawn lines here that show the path that the centers would move along. So if this perimeter of this cell here was too big, we'd move all these centers farther out, and vice versa if it was too small. Here's an example of the code we use. I just want to point out that this is written in a while loop here, so that this right here will compile and create new centers. Then this here will create a new Voronoi and check the perimeter here, and if the perimeter is within a certain tolerance, it will stop. If it's not, it will repeat and spit out new centers until they create a perimeter that is within 0.01% of our tolerance, or 1%, sorry. The next step was to then apply this method and equalize all the cell perimeters, for which we followed the following procedure. So first we would identify the cell that deviated the most from the average perimeter. Then we would look at the neighboring cells and optimize their center locations to make the perimeter equal to the mean. Then we would recreate the Voronoi with these new centers, and then recalculate the mean perimeter, and then repeat. And by doing this, we would have this run in a loop that would continuously compile, and we did this until all centers were within 1% or 0.01 of the mean average, or the mean perimeter. Here you can see an example of before and after. And something I like to note is you can see these boundary centers on the side here look almost as if they're drawn in a bit, and they do not have an equalized perimeter, which is important because this is what we wanted in here to be a representation of what we see in biology. And just a quick look at the code that we used to do this. What we had set up was a while loop that would set the perimeter or calculate the perimeter, figure out which center needs to be adjusted, and then adjust it and repeat until the adjustments made were under a certain tolerance level. The next issue then was storing the data from successive trial runs. And the issue we had here was we were trying to pair trial runs that had data for different sized trials. So an example of this is because our boundary centers, the fact that we have boundary centers that are not included in our data means out of 100 centers, we have a different number of valid centers that we calculate statistics from. So we might have a file that has 65 centers and then another file that has 67 centers. So to put this all together, we use cell arrays, which will compile at the end of every trial run. And an example of a cell array here, as you can see, each individual component of the cell array can take a different sized array itself, which allowed us to compile this data very easily. And now for the results, I'm going to pass it to Emily. Oh, actually, first, I just had a quick thing on the code here. As you can see, an example of this data compilation. This is an example calculation for our angles and areas that happens after every trial run, and then it gets stored, as you can see here, in the cell arrays for angles and area. Now Emily will take over.
Okay, so our initial main question we looked to answer was, do these Voronoi diagrams converge to any sort of solution or set of data? And after running the code hundreds of times and compiling all of this data, we've come to the conclusion that, yes, Voronoi diagrams do in fact converge to several solutions and properties. Some of these solutions are concerning the geometry of Voronoi cells in 2 dimensions, and other solutions are concerning the simulation of cell environment and growth. So the first question we looked at concerning geometry was the distribution of the numbers of sides for a Voronoi cell. And we found that the average length was 0.061, while the average number of edges per cell was 5.8, which matched the literature that we found. The next question we looked at was the distribution of perimeters of Voronoi cells. Now, since we optimized our Voronoi diagrams based on perimeter, with each iteration, the starting perimeters all converged to be within 1% of the same value. So here we have the starting perimeters based on the number of iterations that took place, and we found that they all converged to an average value of 0.388. The next question we looked at was the distribution of area. Since we did not optimize based on area, we have a much wider distribution here. The average area is 0.0092 for each individual inner cell, with a standard deviation of 0.00068. And the last geometry question we really looked at was concerning the distribution of angles within a Voronoi cell. We were actually able to calculate and compile every angle of each cell and observe that the average interior angle was 118 degrees with a standard deviation of 24.38, which also matched the literature that we have found. After solving these initial questions, we used our code to simulate cell environments to better understand the paths growing tissue follow as cells expand and multiply. So cell-to-cell interactions are direct interactions between cell surfaces that play crucial roles in the development and function, such as allowing cells to communicate in response to changes in their environment, like growth. To determine each cell's relation to its neighbor, we calculated the weight, which is the length of the edge that the two cells share. By looking at these weights, one could study where cell-to-cell interactions are most likely or most often to occur in passing of nutrients. Next, another addition within our code calculates neighboring movements of each cell. So we were actually able to calculate how many neighbors each cell has both gained and lost during our optimization process. And we found that the mean change, which includes both gains and losses for each cell, is 3.28, while the standard deviation of that is 2.035. And using this, we can help better understand how cell displacement and interactions during cell growth occur. And lastly, we were able to simulate the addition of a cell to replicate how cells grow during the regeneration process. So how we did this was we basically started with randomly generating 100 points, and then optimizing those 100 points, and then recalling the original random distribution of those 100 points, randomly adding another in, and re-optimizing that diagram as well, and then comparing the two. And by comparing these two diagrams, we can determine how the addition of a cell within regeneration can affect the rest of the cell structure. So overall, we found that the boundary cells, like if you look around here, remain generally the same and in similar places, while the non-boundary cells, the interior cells, have similar patterns that you can see throughout here, but do occur different variances. There's a lot of constraints that we weren't able to consider and we would suggest for future study. Most of these constraints are concerning force-related effects within Voronoi diagrams. So, for example, the conservation of value, how to achieve minimum energy, and maintaining zero balance of forces. Looking at these three pictures on the left, we have a photomicrograph of cells. In the middle here, we have a pattern that's drawn from this photomicrograph showing more clearly the cells. And then here we have an optimized 100-point Voronoi diagram. And just looking at these pictures, we can tell that these Voronoi diagrams do in fact converge to a system that resembles and behaves similarly to cell clusters. And although we have not fully studied the constraints of Voronoi diagrams, we believe that it to be a very good foundation for information and future study. And then here are our acknowledgements for all of the work that we accomplished.